This video is all about vectors. So what is a vector? A vector is a directed line segment defined by its direction and magnitude. Magnitude could also be described as length. Notice there's nothing here about position. So the vector that we see down below there is equivalent to the vector, oops, that doesn't look the same, does it? The vector that has the same direction and magnitude. So those are the same exact vectors. So direction and magnitude are the two defining characteristics. These are used quite a bit in terms of describing forces. The magnitude or the length describes the strength of the force, and the direction describes the direction in which the force is being applied. So I want to state each of these vectors in component form. So notice that we're on a grid here, but we're really not sitting on an XY plane. But we can still think about these as X and Y components. So as I look at this first one, I can see that in the X direction, I've got 1, 2, 3, 4, 5 in the X direction that I need to go in the positive direction. And in the Y direction, I need to move 1, 2, 3. This is reminiscent of the slope, right? So I'm going to go ahead and put it in component form, which is X comma Y. So in component form here, this one is going to be, I go positive 5 and I go negative 3 in the Y direction. Okay, for the next one, I've got my X component. So X component here, notice how I'm starting at the initial point of that vector and I'm moving towards the terminal point of the vector. So in the X direction, I need to move +1. And in the Y direction, I need to move 1, 2, 3, 4 +4. So component form is going to be positive 1 comma 4. Okay, so finally for this one, again, starting at the initial point, I need to move 1, 2, 3, so negative 3 in the X direction, and then positive 1 in the Y direction. So component form here is going to be negative 3 for X and positive 1 for Y. Next, we're going to find the magnitude. Notice how as I found each of these X and Y components, I actually created a triangle. So the magnitude turns out to be the hypotenuse of each of these triangles. So finding the magnitude is actually really easy. We can go ahead and apply the Pythagorean theorem. So we apply the Pythagorean theorem. Let me do it up above here in green. We know that x squared plus y squared is equal to that hypotenuse squared. So we can find the hypotenuse by taking the square root of x squared plus y squared. A lot like our the radius in our polar form. To describe the magnitude, we use bars around the vector name or the vector in component form. So x comma y. So that describes magnitude. Absolute value, also a distance. So same idea there. So to find each of these magnitudes, I need to take the square root of 5 squared plus negative 3 squared. So that's going to be the square root of 25 plus 9, which is radical 34. There's nothing I can simplify there. So my magnitude is the square root of 34. For the next one, the square root of x squared, so 1 squared plus 4 squared, that's going to be the square root of 1 plus 16. Radical 17, again, nothing to simplify. And then finally, I've got 3 squared and 1 squared. So that's going to be negative 3 squared plus 1 squared, 9 plus 1. So that one's going to be the square root of 10. We want to talk about the directional angle as well. So if I were to describe this vector u in terms of its component form, the component form is x comma y. If I were to do the magnitude of vector u, I can say the magnitude of vector u is equal to the square root of, this is the Pythagorean theorem, x squared plus y squared. If I wanted to find this angle, my directional angle, knowing what x and y are, I can go ahead and use a tangent. So tan theta is equal to y over x. So we could say that theta is tan inverse of y over x, but that's only true if theta lives in quadrant 1. Remember that tan inverse will never give us an obtuse angle. So we want to make sure that we're drawing a picture so our angle actually matches the position of the vector. Okay, so we want to find the direction angle for vector -3, 3. I'm going to go ahead and start by graphing it. Sometimes it's easier than having to do a tan inverse or having to do a calculation. So I've got -3 in the x direction, so 1, 2, 3, and 3 in the y direction, 1, 2, 3. It's going to give me a vector here. I'm going to go ahead and just position these at the origin. They could be positioned anywhere. That direction angle is the angle measured from the positive x-axis over. Well, I've got -3 and 3. I have myself a 45, 45, 90 triangle. I know that this is going to be a multiple of pi fourths. So without really doing any additional work, to get to that angle is going to be 3 pi fourths. Next, let's find the direction angle for -2, -5. So I'm going to draw a picture again. -2, -5, everyone's negative in quadrant 3. So -2, 1, 2, 3, 4, 5 is my vector right here. So that direction angle is this one right here. This is not a common triangle, so I know that I do have -5 here and -2 here. So I do need to go ahead and use a tan inverse, knowing that tan inverse is going to land me in quadrant 1 instead. So let's go ahead and do the tan inverse. So I know that my directional angle, and I'm going to put a little prime here because this is actually this blue angle right here. My direction angle is going to be tan inverse of y over x, so -5 over -2. Let's get these guys in, I don't think it said, I'll go ahead and put these in degrees. Let's do degrees. I'm going to grab my calculator and let me make my worksheet just a little bit smaller so I can see everything. And I'm going to go ahead and put this into degrees. So I want mode and change that angle measure to degrees. Okay. So I want to go ahead and apply my tan inverse. So tan inverse of, you can even drop the negative signs if you want, -5 over -2. And I think I've got an extra parenthesis there, so I'm just going to be lazy and add an extra one at the end. I don't think it's going to matter. Yeah, perfect. So I end up with 68.198. I'm going to call that 68.2 degrees. That is this angle right here. That's 68.2 degrees. Instead, I want the angle that's over here. I just need to add pi to it. So the angle that I'm looking for is actually going to be that 68.2 plus pi, or 180 degrees since I'm in degrees. So I'm just going to take this answer. I'm just hitting the plus sign. My calculator knows that I want to do my previous answer, and I'm going to add 180. And that gives me the angle that I was looking for, lands me right into quadrant 3, and I've got 248.2 degrees is my direction angle. So drawing that picture really makes a big difference. Next, I've got an angle for 4, -3. So for 4, -3, 1, 2, 3, 4, 1, 2, 3. This one lands here. I know that my tan inverse will find me the negative angle here, but I actually want the direction angle measured as if I were on like a polar axis. Really, either of the two would be correct, but just as a good rule of thumb, I'm going to go ahead and do the positive value. So let's go ahead and do the tan inverse. Tan inverse will give me a negative value. It can give me anything between -90 degrees and positive 90 degrees. Let's go ahead and do the tan inverse. So I've got a tan inverse of y over x, -3/4. So tan inverse of -3/4, -3/4. So I'm going to get my angle, but it's going to be a negative angle in quadrant 4 there. So this gives me -36.87. I can round that differently as well. Well, these are really nice because I've actually landed on the correct position. I just want to express this instead going counterclockwise. So I'm going to add I'm going to add 360 to this one, just add a full rotation. So I'm going to go ahead and add 360 degrees, a full rotation. So I'm going to add plus 360. So with this picture, I know if I need to add, I know if I need to go ahead and add a full rotation, or if I just need to add half of a rotation to get to the correct answer. So I'm going to go ahead and add 360, and I get the angle that I'm looking for, which is 323 point, we'll call that 323.1. We'll do blue. So 323.1 degrees. Okay, so now I want to take a look at vector operations and linear combinations. I have two different vectors that I've designated here, and you can see that vector v from its initial point goes to the left by 1 and then up by 2, and vector u from its initial position is a 1, 1, so it goes over 1 and up 1. I'm going to go ahead and do u plus v. I can start these in any position. Remember that it's just the direction and magnitude that defines the vectors, not where they sit in a coordinate plane. So I'm going to go ahead and I'll just draw u anywhere. So I need to start with u. So I'm going to go ahead and start with u. And then I want to go ahead and take the tip of vector u and then draw vector v. So I need to go over 1 and up 2. That's going to be right here. So my resulting vector is, let me go ahead and put this in red. My resulting vector, I'm going to go ahead and take my initial point and my final point after I've added these two tip to tip. This is my final vector right here. Let's see, so I want to draw as indicated and state in component form. So this vector in component form, which I didn't do the best job drawing, I'll make it really thick there. So this vector, I don't have any movement left or right in the x direction, so it's going to be 0 in the x direction, but I do move up 1, 2, 3 in the y direction, so 0, 3. Now we're going to do u minus v. Negative v takes the original vector that I've got here, and instead of moving up and to the left, it's just going to completely reverse the direction. So negative v looks like this. So as I draw these vectors, I'm going to go ahead and start with u. And again, you can put u anywhere. I want to leave myself a little bit of room. So there's vector u. I'm going to go ahead and take the tip of that and now do a vector v that's negative. So I'm going to go v, but in the opposite direction. So down 2 and over 1. Now grabbing my red pen, my initial point was here. My final point was here. So my resulting vector is this guy, which is down 1 over 2. So positive 2 in the x direction, down 1 in the y direction. The component form, a lot like a slope. So if you're thinking slope, but then write it in component form, you've got that correct. Next, I've got 2 times u. So I actually want to go 2 of these u vectors. You can also think of 2u as u plus u. We call this 2 out in front a scalar multiple. Scalar is just a real number multiplied by a vector, but it literally means twice the length of u. So that would be twice the length of u. If I were to write it in terms of u plus u, I'm going to end up with the same vector. There's one u, tip to tip, there's the second u, and my resulting vector is the one that we've drawn here, which is this guy. So now I've just doubled the x and the y component. So I need to go 2 in the x direction, 2 in the y direction. So I end up with 2, 2 for its component form. In this next group, we have additions that have been done for us, and we want to go ahead and take vectors u and v and decide exactly what happened. Okay, so for this first one, I notice I'm going to look at the slope, and that's the direction of my vector. So the slope is it's negative, so it's going to be -1, -1. And notice how it's pointing in the opposite direction there. So I've switched the direction of u, and I have doubled its length. So I'm going 2 and 2. So this is going to be -2u. Okay, so next one. So for the next one, gosh, this is again, my slope is still that -1, 1. So I've got my slope there. So this guy right here is 2u, is my negative 2u. And I'm adding, this one is 2 and 1. This is a vector v, but it's going in the opposite direction. So this guy is vector v. So this is negative 2u minus v. Okay, next one. This one has the same slope as u, so I know that this one's going to be a vector u. It has twice its length. So this one is 2u. This one has the same slope as vector v. It's pointing in the opposite direction, and it's twice as long. So this one needs to be a negative 2v. So this is going to be 2u minus 2v. Okay, so finally, it looks like I'm starting with vector u here, and it is just vector u, no changes. So I have vector u, and this is vector v because it has the same slope, but it's twice the length. So this is 2v. So vector u plus 2 times vector v. So just a few more here with a different pair of u and v. So u now is the blue one and v is the green one. So if I want to go ahead and do u plus v, let me go ahead and grab my colors here. U is, there's no change. So I'm just going to, you can draw it wherever. So this one is up 2 over 1. So here's vector u. And then I'm going to go tip to tip. I want to subtract v. Negative v is going to go in the opposite direction. So this guy would be negative v. So negative v lands me right here, and my resulting vector, if I start at the initial point and go to the terminal point, it's right there. So no change in the x direction, so 0x for the x component, and 1, 2, 3 for the y component. Okay, next we want negative 3v. This is negative v right here. So I can go ahead and start with that one, and I want 3 times its length. So if I go ahead and take v, but I want 3 times its length, we end up with this single vector right here. So that's going to be negative 3 in the x direction, positive 3 in the y direction. So this is negative 3 comma 3. And I can go ahead and draw yellow there, making sure I've got my initial point and terminal point correct. Okay, so finally, last but not least, my initial point is right here, and my first vector has a slope of 1, 1. So that's going to match my vector v, but it has twice the length. So this is 2v, 2v. And then this one right here is similar to u, but it's going in the opposite direction. So it does have the same length as u. Whoops, I think I drew that wrong. It does have the same length as u, but it's in the opposite direction of u. So this guy right here is negative u. So 2v minus u.